What began as a handful of engineers wiring together fragile tubes in the 1940s has grown into the most powerful tool humanity has ever built. Tonight, we slow everything down and walk through that evolution step by step. Early mechanical calculators, wartime codebreakers, mainframes, personal computers, the birth of the internet, and the rise of modern AI hardware. By the time sleep arrives, you'll know how the entire digital world came to be. Chapter 1. The Age of Calculation Before Computers Existed. Long before anyone imagined electricity guiding information, humans were already trying to shift mental work into physical tools. The journey toward computing begins not with circuits or metal, but with the basic human need to keep track of numbers, measure quantities, and solve complex problems faster than memory alone could manage. The very first devices were simple, almost primitive by modern standards, yet they carried an idea that would guide every invention that followed: the separation of thought from calculation. The abacus is the earliest well-known example. Its design, built from beads sliding along rods, appears in many cultures: Mesopotamian, Chinese, Greek, each using slight variations to represent larger values, perform addition, or run quick conversions. It was portable, dependable, and far quicker than mental arithmetic alone. Even though it wasn't programmable in any modern sense, it represented the first external processor of human reasoning. An abacus user could solve a problem faster and more accurately than someone computing mentally, which is the exact advantage we expect from computers today. Mechanical calculation took a significant step forward in the 17th century through the work of thinkers like Blaise Pascal and Gottfried Wilhelm Leibniz. Pascal's Pascaline and Leibniz's stepped drum mechanism were attempts to automate addition, subtraction, multiplication, and division using gears, rotating wheels, and carefully aligned teeth. These machines were expensive, fragile, and limited, but they carried a deeper implication. Machines could not only store numbers, they could manipulate them. That shift planted the first seed for the programmable systems that would appear centuries later. By the early 1800s, Europe had grown increasingly dependent on accurate mathematical tables for navigation, engineering, and astronomy. Errors were common and sometimes catastrophic, threatening ships, construction projects, and economic planning. This slowly created a demand for reliable mechanical computation at a scale beyond human clerks. The environment was ready for a major leap, and one man stood at the center of that transition: Charles Babbage. Before Babbage built anything approaching a modern computer, he began with the difference engine, a massive machine designed to automatically compute polynomial functions and produce printed numerical tables. Although the full version was never completed in his lifetime, its design was astonishingly advanced. It used cranks, columns of gears, and meticulously arranged components to eliminate human error and replicate the precise steps of mathematical algorithms. More importantly, it demonstrated that calculation could be broken down into deterministic mechanical operations, a principle that modern computing still follows. Alongside these developments, the idea of programmability quietly emerged from a surprising source: weaving. Joseph Marie Jacquard's automated loom, invented in 1804, used punched cards to control complex textile patterns. Each card represented a specific operation, allowing weavers to program patterns without manually controlling each thread. This was arguably the first real-world example of encoded instructions controlling a machine, and it helped Babbage envision an even more ambitious system: a general-purpose mechanical computer. The environment in which these ideas formed was one of rapid industrial expansion. Factories were growing, engineering demands were rising, and societies were beginning to recognize the limits of human computation. While none of these early inventions resembled electronic computers, each one contributed a key component of the intellectual foundation. The abacus proved the usefulness of external calculation. Pascal and Leibniz showed that mechanical devices could perform arithmetic autonomously. Jacquard demonstrated that machines could follow stored instructions, and Babbage attempted to merge all these concepts into a single programmable system. This early era also highlights a crucial pattern in computing history. Progress often outpaces the available technology. Many 17th and 18th century inventions worked in theory, but failed in practice due to material limits, cost, or the difficulty of building precise mechanical parts. Yet the ideas persisted, waiting for engineering and physics to catch up. When electricity arrived, everything would change, but the logic guiding modern machines was already forming. This chapter ends just before the emergence of true computing. The groundwork has been laid. Humans want machines that can store information, follow steps, and remove human error. With this foundation in place, the next step is to introduce the individuals who would define the conceptual blueprint of programmable computing. Charles Babbage, Ada Lovelace, and others who understood the deeper possibilities behind mechanical logic. Chapter 2. The Dawn of Computing, Babbage, Ada, and the First Concepts. By the early 19th century, the industrial world was changing fast enough that mathematics could no longer keep up. Railroads, steam engines, shipping routes, engineering projects, everything depended on calculations that were massive in scale and easy to get wrong. Human computers worked in teams to generate tables of logarithms and trigonometric values, but mistakes crept in everywhere. A single incorrect digit buried in a long table could misguide a 2P ship, destabilize a bridge, or ruin a business forecast. The need for reliable automated computation was becoming undeniable, and this pressure created an environment where bold ideas could flourish. Charles Babbage entered this scene with the mindset of an inventor and the frustration of a perfectionist. After reviewing printed mathematical tables filled with errors, he famously remarked, "I wish to God these calculations had been executed by steam." That single frustration led him to design the difference engine, a massive mechanical calculator intended to produce perfectly accurate tables. It used a method called finite differences to approximate polynomial functions, transforming complex math into a sequence of repeated additions. Each wheel, gear, and column represented a digit, and the machine advanced through calculations by turning a crank or, in future designs, by steam power. The concept was groundbreaking, a physical device following deterministic steps without human intervention. But Babbage's genius wasn't limited to building a calculator. As he worked on the difference engine, he became increasingly absorbed in a far more ambitious idea, a machine capable of performing any calculation, not just a single class of functions. This led to the design of the analytical engine, the true ancestor of the modern computer. It was never built, but its architecture contained elements found in every digital computer today: a processing unit, memory, branching logic, loops, and programmable instructions. Babbage had imagined a fully general-purpose machine long before the technology existed to construct one. The analytical engine contained 4 major components, each with a clear modern counterpart. The mill served as the processing unit, performing arithmetic and comparisons, essentially a conceptual CPU. The store held numbers for later use, functioning like memory. The reader interpreted punched cards containing instructions, much like modern input devices or programs. Finally, the printer produced results automatically. Even the terminology reflected computational thinking, suggesting Babbage intuitively grasped the future structure of machines that wouldn't exist for more than a century. While Babbage had the architecture, another figure helped reveal what that architecture truly meant. Ada Lovelace, daughter of the poet Lord Byron, worked with Babbage after examining his designs and attending his demonstrations. She possessed a rare combination of mathematical skill and imaginative insight. Where others saw mechanical gears performing arithmetic, she saw the possibility of symbolic manipulation. Her notes on the analytical engine weren't just commentary. They laid out concepts that would define programming itself. Ida's most famous contribution is often called the first computer program. a detailed method for calculating Bernoulli numbers using the analytical engine's capabilities. But her real legacy comes from the ideas embedded in her writing. She understood that the machine was not restricted to numbers alone. It could operate on symbols and instructions in the same structured way. In her words, the machine weaves algebraic patterns just as a loom weaves textiles, showing a clear analogy to the Jacquard punch card system. She also described the separation of data and operations, the essence of modern computing logic. More importantly, Ada anticipated that computational machines would eventually be able to create outputs that surpassed simple arithmetic. She speculated they could produce music, images, and patterns if the rules governing those systems were encoded properly. This insight predated electronic computers, circuits, or even formal logic systems. It was essentially a prediction of general-purpose computation, multimedia processing, and algorithmic creativity, a vision far ahead of her time. Despite these conceptual breakthroughs, the analytical engine never became a working machine. The technology of the 1800s was simply too limited. Precision engineering at the required scale was costly, and manufacturing errors could ruin the intricate gearwork. Babbage struggled with funding, disagreements with engineers, and political obstacles. His designs were brilliant, but 19th-century mechanical engineering wasn't ready for a device of such complexity. The Industrial Revolution produced steam engines, textile mills, and locomotives, but it couldn't yet produce a computational machine with thousands of interlocking parts, fine enough to function reliably. Although the analytical engine remained theoretical, its impact was significant. The diagrams, notes, and explanations preserved the idea of a programmable machine for the next generation of thinkers. When electricity eventually entered the picture, Babbage's conceptual foundation fit perfectly into emerging scientific progress. While most 19th-century inventions rose and fell with their creators, Babbage's work survived as a blueprint waiting for its moment. After Babbage and Lovelace, mechanical computing continued in more practical and specialized forms. Herman Hollerith's punched card tabulating machines, designed in the late 1800s, were used to process the 1890 United States Census. Hollerith developed a system that encoded information as wholes on cards, which could be sorted, counted, and analyzed automatically. This innovation increased the speed of census processing dramatically, saving years of manual labor. More importantly, it sparked a business that would eventually become IBM, a company that would dominate computing throughout the 20th century. These tabulating machines were not general-purpose computers, but they demonstrated the power of automated information handling. For the first time, machines weren't just doing math. They were organizing, categorizing, and processing data at a national scale. This shift from calculation to information management foreshadowed modern computing far more than the mechanical calculators of earlier decades. This chapter marks the moment where computing transitions from scattered mechanical experiments to fully articulated ideas. Babbage provided the architecture. Ada provided the conceptual meaning behind programmability. Hollerith provided the early industrial application. Everything was now in place except the one ingredient mechanical systems lacked: electricity. Once that arrived, computing would accelerate faster than anyone could have predicted. Chapter 3: War, Codebreaking, and the Birth of Modern Machines. When the 20th century opened, computation was still rooted in mechanical devices. Tabulators sorted punched cards, calculators performed arithmetic with gears, and large organizations relied on specialized machines for accounting or statistics. But these devices were limited in flexibility, speed, and scope. Compared to Babbage's vision, they were powerful tools, but not true computers. It took a global crisis, 2 world wars, to push technology past its mechanical boundaries. Under pressure, innovation accelerates, and nowhere was this more evident than in the computational demands of cryptography, ballistics, communication, and logistics. World War II created challenges that no existing calculation methods could handle quickly enough. Artillery trajectory tables had to be generated and updated rapidly. Encrypted communications needed to be deciphered before the information became irrelevant. Radar systems produced raw data that had to be processed in real time. Supply chains stretched across oceans and required continuous planning. Human clerks and mechanical tabulators simply could not keep pace. Nations turned to scientists, mathematicians, and engineers, giving them unprecedented freedom and funding to create new machines capable of processing information faster than ever before. One of the most important breakthroughs of this era occurred at Bletchley Park in the United Kingdom, where a team led by Alan Turing, Gordon Welchman, and other cryptanalysts worked to break the German Enigma cipher. Enigma's complexity came from rotors that shifted the mapping of letters with each keystroke, producing an astronomical number of possible configurations. Manual decoding was impossible within a useful time frame. To address this, the British developed the bombe, an electromechanical device that tested Enigma settings at far greater speeds than humans could. While the bombe did not resemble a modern computer, it wasn't programmable in a general sense. It automated logical reasoning and search algorithms, reducing decryption times from days to hours. But for truly electronic computation, another machine was needed. That machine was Colossus, built under the direction of engineer Tommy Flowers. Colossus was the world's first large-scale, programmable electronic computer. Unlike previous devices, it used vacuum tubes to perform logical operations at speeds that mechanical components could never achieve. Colossus analyzed encrypted messages intercepted from German teleprinter systems using a statistical algorithm known as pattern counting. It read data from punched paper tape at remarkable speeds and applied logic circuits to test possible key values. Colossus was not a fully general-purpose computer. It couldn't store programs in memory or execute arbitrary instructions, yet its architecture introduced foundational elements of modern digital logic: electronic gates, switching circuits, Boolean operations, and high-speed data scanning. It demonstrated that computation no longer had to rely on physical gearing or mechanical timing. Instead, electrons flowing through circuits could represent information and logic. This shift was transformative. Although Colossus remained classified for decades, its success proved that large-scale electronic computation was possible and reliable. Across the Atlantic, the United States was tackling different computational challenges, including the complex differential equations needed for ballistics research. The result was ENIAC, Electronic Numerical Integrator and Computer, completed in 1945. While ENIAC was not initially designed for cryptography, it ended up being used for hydrogen bomb calculations, weather prediction research, and other advanced scientific work. ENIAC contained nearly 18,000 vacuum tubes, was programmable through plug boards and switches, and could perform calculations thousands of times faster than electromechanical devices. ENIAC was not a stored program machine. Programs had to be physically rewired using cables, but its performance was unprecedented. It showed that electronic computation could support scientific research, engineering, and military applications at a scale humans had never seen. It also introduced an important cultural shift. Governments and research institutions began to rely on computers as strategic tools, not simply mechanical conveniences. The idea of a stored program computer emerged shortly afterward from mathematician John von Neumann and his collaborators. They proposed an architecture in which instructions and data were stored in the same electronic memory, allowing programs to be changed without rewiring. This would become the foundational design of nearly all modern computers. While ENIAC hinted at this possibility, its successors, including EDVAC and EDSAC, were built explicitly around this new architecture. These machines demonstrated that programs could be written in symbolic form, loaded into memory, and executed automatically, just as Babbage had envisioned a century earlier. War accelerated development not only technically, but also organizationally. Large teams of mathematicians, engineers, electrical specialists, and industrial partners worked together under intense deadlines. This collaborative model foreshadowed the corporate and academic research environments that would drive computing progress in later decades. It also helped standardize the language of digital logic, bits, gates, registers, and sequences, which would become universal concepts once electronic computers entered the civilian world. As the war ended, the machines built during this period laid the groundwork for every generation of computers to come. Colossus proved electronic logic could scale. ENIAC demonstrated high-speed numerical computation. The stored program concept unified architecture into a workable model. Governments saw the strategic value of computing and continued funding research. Private companies realized that demand existed beyond military use, and universities began creating programs to train a new type of engineer, one who understood both mathematics and electronics. By the late 1940s, the world stood on the edge of a new era. Computing was no longer a theoretical possibility or a mechanical curiosity. It was a working reality, driven by vacuum tubes, enormous rooms of equipment, and newly formalized programming methods. But these early machines had serious problems. They were expensive, prone to failure, consumed enormous amounts of power, and required constant maintenance. Vacuum tubes burned out regularly, causing unpredictable downtime. Memory was limited, slow, and difficult to manage, and programs had to be written extremely carefully to work within the constraints of early architecture. The next major shift would remove these limitations almost overnight. As researchers began experimenting with new materials and smaller components, the path opened toward more stable, efficient, and compact machines. The vacuum tube era had proven a concept. The coming transistor era would transform it into a practical, reliable foundation for computing as we know it. Chapter 4. Vacuum tube computers. The room-sized era begins. When the war ended, the world entered a strange moment where computing was both incredibly advanced and incredibly fragile. Machines like ENIAC and Colossus had already proven what electronics could do, but they were closer to experimental prototypes than practical tools. They filled entire rooms, hummed loudly, gave off enormous heat, and burned through components at an exhausting pace. Yet despite their limitations, these early vacuum tube systems marked the beginning of computing as an actual profession and industry. They were no longer wartime secrets or temporary solutions. They were the first generation of machines meant to exist beyond emergency circumstances. Vacuum tubes were the heart of these early computers. Before transistors, they were the only reliable way to electronically amplify signals and switch currents on and off. Each tube could represent a bit as either conducting or non-conducting, effectively functioning as a primitive electronic switch. But tubes were large, fragile, and power-hungry. A single computer contained thousands of them, meaning daily failures were expected. A technician's job often involved walking through rows of cabinets, listening for faint pops, looking for dimming glow, or simply waiting for the machine to stop functioning before isolating the faulty component. Even so, the speed advantage over mechanical systems was overwhelming. What once took hours or days could now be solved in minutes. This era produced several landmark machines. EDVAC, proposed during the final stages of ENIAC's development, was one of the first computers designed around the stored program concept. Though not completed as quickly as planned, its design circulated widely and influenced nearly every early computer that followed. In the United Kingdom, EDSAC ran its first program in 1949. It was one of the earliest fully operational stored program machines and helped solidify best practices for memory, instruction sets, and subroutines. EDSAC also supported academic research, making it one of the first computers to produce scientific results that were not directly tied to military or cryptographic needs. Meanwhile, the United States developed UNIVAC-Y, completed in 1951. UNIVAC was the world's first commercially produced computer, a machine built not for research laboratories, but for actual clients. Its creators, J. Presper Eckert and John Mauchly, believed that businesses, governments, and scientific organizations would soon demand computational power. They were correct. UNIVAC systems were used for census processing, insurance calculations, and even famously predicted the outcome of the 1952 U.S. presidential election on live television. For many viewers, this moment marked the first time they saw a computer as something more than a mysterious machine hidden away in a government facility. It was a sign that electronic computation would soon touch ordinary life. Early memory technologies were just as important as logic circuits. Vacuum tube computers often relied on delay line memory, long tubes filled with mercury that stored data as sound waves bouncing back and forth. Others used Williams tubes, which stored bits as charged spots on the face of a cathode ray display. These methods were clever but unstable, requiring constant calibration. Engineers and operators spent long hours maintaining memory performance, often adjusting equipment by hand. Still, these structures allowed programs to store data dynamically and allowed larger programs to be written in more complex forms. Programming itself was undergoing a revolution during this time. Instead of rewiring machines by hand, operators began to write instructions in symbolic language that could be assembled or interpreted by the computer. These early languages were primitive by modern standards, but they created an entirely new profession. Programmers emerged as a specialized workforce, often composed of mathematicians and, notably, many women who had worked as human computers during the war. Their skills became invaluable as machines grew more complex, and they formed the foundation for modern software development. The vacuum tube era also defined how computers were physically organized. Cabinets were arranged in long rows filled with wires, tubes, transformers, and switching components. Massive power supplies and cooling systems were necessary to prevent overheating. Punch cards and paper tape served as primary input methods, while early printers and teleprinters produced output. These design patterns influenced all subsequent computer rooms, from the mainframe halls of the 1960s to the data centers of today. The image of rows of tall machines with blinking lights originates from this era. Despite their size and cost, early computers were transformative. They automated calculations that had previously consumed vast human effort. They allowed scientists to model physical systems, simulate equations, and run statistical analyses that were previously impossible. Governments used them for census management, code-breaking, logistics planning, and economic modeling. Businesses used them for accounting, inventory tracking, and financial forecasting. For the first time, computation was becoming a generalized tool, something that could be applied to many problems, not just specialized ones. Yet the vacuum tube era was never meant to last. As engineers learned more about semiconducting materials, it became clear that vacuum tubes were a temporary solution. Tubes were too large, too unreliable, and too expensive for mass adoption. The machines of the 1950s hinted at what computing could become, but they still belonged to institutions with substantial budgets and technical staff. The next breakthrough, a device far smaller and more stable than a vacuum tube, would bring the power of computation to a far wider audience. That breakthrough was the transistor, and its arrival would mark the beginning of the second generation of computers. With it came lower costs, greater reliability, and dramatically reduced power consumption. Instead of rooms full of glowing tubes, computers could be built using tiny solid-state switches, opening the door to systems that were faster, smaller, and far more capable. It would not be long before the transistor completely reshaped the landscape that vacuum tubes had built. The vacuum tube era remains essential to computing history because it proved the feasibility of electronic logic and established the architectural principles used to this day. It showed that digital machines could solve meaningful problems, that programming languages could exist, and that computation could support science, business, and government. It laid the groundwork for everything that followed. The next chapter would show what happens when the same principles are carried forward using new materials that would take computation from fragile experiments to dependable tools. Chapter 5. Transistors and the Rise of the Second Generation. By the early 1950s, one fact had become unavoidable. Vacuum tubes could take computing only so far. They enabled the first electronic computers, but they were fragile, energy-hungry, and physically enormous. A machine with 18,000 tubes could run ballistic equations for the U.S. Army, but it couldn't sit on a desk, survive long hours without maintenance, or scale affordably. Engineers and scientists had reached a kind of technological ceiling. To break through it, they needed a completely new kind of switch, one that didn't burn out, didn't require warm-up time, and didn't glow red-hot just to perform a logical operation. That breakthrough came in 1947 at Bell Laboratories, when John Bardeen, Walter Brattain, and William Shockley created the first transistor. This tiny device, made of germanium, could amplify electrical signals and act as a switch, just like a vacuum tube, but it did so without any moving parts or fragile filaments. It was smaller, faster, cooler, and far more durable. At first, the transistor was simply seen as an improvement for telephones and radios, areas where Bell Labs had direct interest. But engineers around the world quickly recognized that this new component could redefine what electronic computers looked like. The first transistorized computers appeared in the mid-1950s. They were still large, still expensive, and still built for institutions. But they were dramatically more reliable than their tube-based predecessors. Instead of thousands of components burning out every few days, transistors ran for long stretches with minimal failures. Machines no longer required constant supervision. They could be powered on for extended periods without fear of catastrophic tube failures. This stability was a turning point. It meant that computers could now be used not just for specialized tasks, but for continuous operations that required predictable uptime. One of the earliest fully transistorized computers was Tradic, developed by Bell Labs in 1954. It contained over 700 transistors and demonstrated the new technology's potential for speed and efficiency. Meanwhile, IBM, already a giant in mechanical tabulators, saw the writing on the wall and began investing heavily in transistorized systems. The IBM Postino-1, released in 1959, became one of the first commercially successful transistor computers adopted by thousands of businesses. For many organizations, the 1401 was their first real introduction to electronic data processing. Its success marked the beginning of computing as an industry accessible beyond governments and elite laboratories. Transistors also revolutionized the design of computer memory. Instead of unstable technologies like mercury delay lines or Williams tubes, second-generation machines adopted core memory, built from tiny magnetic rings strung on wire grids. Each ring stored 1 bit, and its magnetic orientation could be flipped rapidly by electrical pulses. Core memory was durable, fast, and non-volatile, meaning data remained stored even when the power turned off. This reliability made computers more practical for business use, where programs and data needed to remain intact between sessions. Programming languages advanced rapidly during this era, too. Early symbolic languages had proven the concept, but now the field matured. Grace Hopper developed COBOL, designed for business applications and readable by non-mathematicians. John Backus and his team created Fortran, a language suited for scientific and engineering calculations. These languages allowed programmers to write in more natural syntax, while compilers translated human-written code into machine instructions. This shift dramatically increased productivity and opened programming to a wider range of people. The idea of software began to take shape as something distinct from hardware. Meanwhile, the idea of an operating system emerged. Instead of loading each program manually and managing memory by hand, computers began running supervisory software that handled input, output, scheduling, and resource allocation. This laid the foundation for the multitasking and memory-managed systems that later became standard. Though primitive compared to modern standards, these early operating systems transformed computers from single-task machines into flexible platforms capable of running multiple jobs in sequence. The transistor era also established the first true computer industry. Companies competed not only on performance but on ecosystems, languages, support services, peripherals, and business solutions. IBM, Honeywell, Burroughs, Univac, NCR, and Control Data Corporation became known collectively as the Seven Dwarfs, competing with IBM's rapidly expanding market share. Universities began offering formal degrees related to computation. Research institutions used computers to explore physics, meteorology, genetics, and economics. Corporations adopted computers for payroll, billing, logistics, and forecasting. The idea that digital machines could replace entire departments of clerks and analysts shifted from speculation to reality. Transistors shrank more quickly than anyone expected. Engineers found ways to manufacture them more efficiently, making them smaller, cheaper, and more consistent. Each improvement in transistor design enabled computers with greater speed, larger memory, and more powerful instruction sets. As manufacturing matured, the cost per transistor dropped dramatically. This trend, falling cost, rising performance, hinted at something profound. If transistors kept getting smaller, there might be no practical limit to how powerful computers could become. The turning point came in 1958, when Jack Kilby at Texas Instruments built the first integrated circuit, IC. A year later, Robert Noyce at Fairchild Semiconductor created a more manufacturable version. Instead of wiring transistors, resistors, and capacitors together by hand, the integrated circuit placed them on a single piece of semiconductor material. This was more than a technological step. It was a complete rethinking of how computers were built. The IC removed the need for individual assembly of components. It allowed thousands of transistors to be created at once, with precise micro-scale structures etched onto silicon wafers. Integrated circuits didn't immediately replace all transistor designs, but their impact was irreversible. As they became more reliable and easier to mass-produce, computer designs shifted again, from discrete transistor machines to IC-based architectures. This set the stage for the next generation, smaller machines that could fit in offices, laboratories, and eventually homes. By the early 1960s, the second generation was firmly in place. Transistorized computers were handling social security data, managing airline reservations, calculating scientific models, and running financial institutions. They were far faster, more stable, and more compact than their vacuum tube predecessors. They proved that reliable electronic computing was not just possible, it was scalable. Still, even these machines occupied full rooms and cost significant sums. True miniaturization had not yet arrived, but everything was in motion. Transistors had shrunk the giant vacuum tube systems drastically, and integrated circuits were poised to shrink them further. The idea of a computer small enough to fit on a desk no longer felt like science fiction. The ingredients for the next leap, the age of minicomputers and microchips, were already falling into place. The transistor era proved one thing beyond any doubt: computation could be affordable, dependable, and adaptable. Once those three qualities existed simultaneously, computing was no longer an experiment. It was an industry with unstoppable momentum. Chapter 6: Integrated Circuits and the Rise of Minicomputers. By the early 1960s, the invention of the integrated circuit, IC, had quietly planted the seeds of a technological transformation. At first glance, these early chips did not look revolutionary. They contained only a handful of transistors, sometimes just 2 or 3, etched onto a thin slice of silicon. But the principle behind them, that circuits no longer needed to be built component by component, was profound. Instead of assembling thousands of tiny parts manually, engineers could now design an entire logical function, place it on a wafer, and replicate it endlessly with remarkable consistency. This consistency mattered more than anything. Machines built from discrete transistors had impressive performance, but as the number of transistors grew, so did the potential for failure. Integrated circuits allowed computers to become more complex while maintaining reliability. They also enabled dramatic reductions in size, cost, and power consumption. A computer that once required many cabinets could now be built with fewer boards, fewer connections, and far fewer points of failure. This was the foundation upon which the next era of computing, the minicomputer era, would rise. The first widely successful minicomputer arrived in 1965, the PDP-8, created by Digital Equipment Corporation, DEC. It cost a fraction of what IBM's large systems demanded and was small enough to fit on a desk or into a lab environment. Universities purchased it for research. Laboratories used it for instrument control. Small businesses adopted it for accounting and process automation. Although still expensive by modern standards, the PDP-8 represented a psychological breakthrough. Computers no longer belonged exclusively to corporate giants or government agencies. A computer could serve a specific team, department, or project, rather than an entire institution. DEC's success did not happen in isolation. The integrated circuit was rapidly improving, following a trend that Gordon Moore observed in 1965, a pattern that would later be called Moore's Law. Moore noted that the number of components on an integrated circuit seemed to double roughly every year, later refined to every 18 to 24 months. This was not just an observation about manufacturing progress. It was a prediction that computing power would grow at an exponential rate while costs continued to fall. Although no physical law required this pace, the entire semiconductor industry adopted it as a guiding principle, turning Moore's observation into a self-fulfilling prophecy. Minicomputers thrived in this environment. DEC followed the PDP-8 with the PDP-11, one of the most influential computers ever created. The PDP-11 introduced an elegant and flexible architecture, widely admired for its simplicity and power. It supported emerging operating systems, including the one that would eventually dominate decades of computing innovation, Unix. Created at Bell Labs in 1969 by Ken Thompson, Dennis Ritchie, and their colleagues, Unix was built to be simple, modular, portable, and efficient. The philosophy behind it, that software should be constructed from small, composable tools, influenced nearly every operating system that followed. Meanwhile, other companies built their own mini-computers, shaping a vibrant environment of competition and innovation. Hewlett-Packard developed programmable scientific computers used in laboratories and engineering firms. Data General introduced the Nova series, which powered industrial and scientific applications. Honeywell, Burroughs, and other companies expanded the range of available systems, creating machines suited for everything from manufacturing control to academic research. Integrated circuits were steadily improving during this time. Early ICs were small-scale integration, SSI, containing only a handful of logical gates. Soon, medium-scale integration, MSI devices, arrived with dozens of gates. Then large-scale integration, LSI, with hundreds, and later very large-scale integration, VLSI, with thousands. As chips grew more capable, the complexity of systems built from them increased accordingly. A single board that once held dozens of logic modules could now be replaced by a handful of high-density chips. This reduction in component count improved reliability and opened the doors to more compact system designs. The minicomputer era also reshaped organizational computing. Instead of submitting jobs to a central mainframe and waiting for batch results, teams could interact directly with their own machine. This encouraged experimentation, software development, and rapid testing. Interactive computing, typing commands and receiving immediate feedback, began to flourish. Terminals replaced punch cards. Programmers moved from batch workflows to conversational sessions with time-sharing systems. This shift in user experience was fundamental. It laid the groundwork for the personal computing revolution that would follow. Scientific research benefited enormously from minicomputers. Molecular modeling, physics simulations, and astronomical calculations became more accessible. Minicomputers controlled telescopes, ran lab instruments, and supported early data acquisition systems. In industry, they managed manufacturing processes, chemical plants, and industrial automation systems. Their relative affordability meant they could be deployed widely, forming the backbone of many technical and engineering workflows. The military and aerospace industries also played a major role in advancing integrated circuits. Spacecraft, missiles, and aircraft required computers that were compact, lightweight, and resistant to changing environmental conditions. NASA's Apollo guidance computer, while not built with modern ICs, demonstrated how compact computer systems could guide spacecraft beyond Earth's orbit. This project accelerated research into miniaturized computing and contributed to the development of increasingly dense integrated circuits. By the early 1970s, the landscape of computing had transformed. Mainframes still ruled large corporate and government environments, but minicomputers were everywhere else, in laboratories, hospitals, engineering firms, and universities. Integrated circuits continued to advance. Manufacturers learned to print increasingly complex patterns onto silicon wafers, creating higher transistor densities and more capable chips at lower cost. This trend was unstoppable. The more circuits manufacturers could fit onto a chip, the more computing tasks could be condensed into ever smaller packages. It was only a matter of time before engineers asked a simple but world-changing question. If an entire CPU could fit onto a circuit board, then why not fit it onto a single chip? The answer would arrive soon, and it would redefine the future of computing. As the 1970s dawned, the next leap was within reach. The principles of integrated circuits had been proven. Minicomputers had opened the market to smaller organizations, and semiconductor manufacturing had accelerated to an unprecedented pace. The industry was on the edge of the microprocessor revolution, a development that would ultimately bring computing power to the mass market, transform global society, and reshape everyday life. Chapter 7: Microprocessors and the Birth of Personal Computing. By the early 1970s, the integrated circuit had already reshaped the computer industry. Systems were smaller, faster, and more efficient than ever before. But one barrier remained. Even the most compact minicomputer still required multiple boards, filled with dozens of chips. A central processing unit was not yet a single entity. It was a collection of interconnected modules. Engineers began to wonder whether the entire heart of a computer could be condensed onto one piece of silicon. If that were possible, size, cost, and complexity would collapse all at once, and computing, which had spent decades moving from rooms to racks to cabinets, could suddenly shrink to something far more personal. The breakthrough came in 1971 with the Intel 4004, the world's first commercially available microprocessor. Designed initially for a calculator company, the 4004 condensed the logic of a CPU onto a chip barely the size of a fingernail. It contained 2,300 transistors, a small number by modern standards, yet it could execute instructions, manipulate data, and control operations just like the much larger processors in minicomputers. It wasn't powerful, but it was proof that an entire processing unit could exist on a single slice of silicon. Intel quickly followed with the 8008 and later the 8080, chips powerful enough to run small computing systems beyond calculators. The 8080 became the engine behind one of the earliest personal computers, the Altair 8800, released in 1975. The Altair looked nothing like modern PCs. It had no keyboard, no monitor, and no elegant case. Instead, it was a blue metal box with an array of switches and blinking LEDs. Programs were entered manually in binary, one switch at a time. Yet the Altair captured something significant: imagination. It suggested that computing could leave the realm of institutions and enter the home. For the first time, everyday people, hobbyists, engineers, students, could buy a computer, assemble it, and shape what it could do. This excitement helped spark one of the most influential communities in computing history, the Homebrew Computer Club in California. Every few weeks, enthusiasts gathered to share ideas, modify hardware, and exchange software. Among these hobbyists were two young men, Steve Wozniak and Steve Jobs, who would soon create a computer designed not for switches and binary code, but for real interaction. Wozniak built the Apple I, a small board powered by the MOS 6502 microprocessor. It came as a fully assembled motherboard, a major leap from the Altair's kit-based design. Jobs envisioned selling it as a product, and together they founded Apple Computer. Soon after, the Apple II arrived, one of the first personal computers with color graphics, expansion slots, and a plastic case. It plugged directly into a household television and allowed people to run games, write programs, and store data on floppy disks. Unlike many machines of its time, it looked friendly, inviting, and complete. Its success began to legitimize personal computing as a real market. But Apple wasn't alone. In 1977, three influential systems arrived almost simultaneously: the Apple II, the Commodore PAT, and the Tandy TRS-80. Known collectively as the 1977 Trinity, these machines moved personal computing from niche hobby to mainstream curiosity. They were used in schools, small businesses, engineering labs, and homes. People learned programming on them using BASIC, a language designed to be simple enough for newcomers, but powerful enough for meaningful projects. For millions of people, these early personal computers created a new sense of possibility. The idea that computers could be tools for creativity, study, productivity, and entertainment. Meanwhile, microprocessors evolved rapidly. Intel released the 8086 in 1978, along with the compatible 8088, which powered a machine that would define corporate computing for decades. The IBM PC launched in 1981. The IBM PC was modular, standardized, and built from off-the-shelf components. For software developers, this standardization created a stable target, one machine architecture that many companies could write programs for. As clones of the IBM PC emerged, the platform spread across the world. It became the backbone of business computing, scientific research, and eventually home computing as well. The arrival of microprocessors also transformed operating systems. Early machines used simple monitors or basic interpreters, but the growing complexity of hardware demanded more sophisticated software. In 1981, a small company named Microsoft provided IBM with a disk operating system called MS-DOS. This system, with its command line interface and simple file structure, became the basis for millions of machines worldwide. A new software industry emerged as developers created spreadsheets, word processors, databases, and games. One of the most influential programs of this era was VisiCalc, the first spreadsheet program. Released for the Apple II, VisiCalc showed businesses that personal computers weren't just curiosities. They were powerful tools that could automate calculations, model finances, and support decision-making. Sales of computers rose dramatically as companies realized that a machine costing a few $1,000s could replace days of manual accounting work. Throughout the late 1970s and early 1980s, microprocessors continued to improve following Moore's law. Each new generation packed more transistors, higher clock speeds, and more efficient designs. Personal computers gained better graphics, larger memory, and more responsive interfaces. Floppy disks replaced cassette tapes, then hard drives replaced floppies. Monochrome monitors gave way to color displays. Keyboards, mice, and early graphical interfaces began shaping the way people interacted with their machines. By the mid-1980s, the idea of a computer in every home was no longer far-fetched. Machines were becoming smaller, friendlier, and more powerful each year. Families used them for homework, games, and learning. Businesses relied on them for spreadsheets and word processing. Schools taught programming to students. The microprocessor had accomplished what few technologies had before. It democratized computing, distributing it from institutions to individuals. The stage was now set for the next great transformation in computing. Microprocessors had made the personal machine possible, but the software that ran on those machines was about to become more intuitive, more visual, and more accessible, ushering in the age of graphical user interfaces and the modern desktop environment. Chapter 8: Graphical Interfaces, Home Computing, and the Software Boom. As personal computers spread through homes, schools, and offices in the early 1980s, one challenge became increasingly visible. Most people did not want to memorize commands. They did not want to navigate file systems using typed prompts or learn long sequences of syntax. The command line was powerful, but it required precision and patience. For computing to truly reach a general audience, it would need a new interface, one based on intuition rather than memorization. This shift began decades earlier at the Xerox Palo Alto Research Center, PARC. In the 1970s, researchers at PARC developed a revolutionary concept, the Graphical User Interface, GUI. Inspired by metaphors from the physical world, desktops, folders, windows, icons, the GUI allowed users to interact with digital information visually. A pointing device called a mouse let users move a cursor, choose options, and manipulate objects on the screen. Instead of typing commands, users could click, drag, and navigate visually. This was a profound change in how people thought about computers. But the machines at PARC were expensive research prototypes, not commercial products. Apple was one of the first to bring this idea to consumers. After visiting PARC and seeing the demonstrative work on GUI systems, the company began designing its own versions. In 1983, Apple released the Lisa, an ambitious but costly machine. While technologically impressive, its high price kept it out of reach for most consumers. The true breakthrough came 1 year later, in 1984, with the release of the Apple Macintosh. The Macintosh was far more affordable than the Lisa, and it introduced millions to the ease of point-and-click computing. Its graphical desktop, bundled with tools like Mac Paint and Mac Write, made computers feel approachable, even creative. Meanwhile, Microsoft recognized that graphical interfaces were the future. Although MS-DOS dominated the early IBM PC market, Microsoft began developing a GUI layer that could run on top of DOS. This project became Windows, first released in 1985. Early versions were limited, but each iteration grew more capable. By the time Windows 3.0 arrived in 1990, followed by the highly successful Windows 3.1, graphical interfaces became standard in the PC world. Users could now navigate files, run software, and manage tasks without touching the command line. Personal computing became not just technological, but experiential. The GUI revolution coincided with an explosion in consumer software. Developers now had a rapidly growing audience of non-technical users. Programs for word processing, spreadsheets, database management, and presentations became essential tools for workplaces. Microsoft Word and Excel began their long rise to dominance. Graphic design tools, music software, educational programs, and early animation tools expanded what computers could do. Entire industries shifted as software replaced mechanical and human processes. Accountants used spreadsheets instead of ledgers. Designers used digital drawing programs instead of drafting tools. Students typed essays instead of handwriting them. Games also played a tremendous role in popularizing home computing. Titles like SimCity, Prince of Persia, Myst, and Doom demonstrated the creative potential of software. They pushed hardware to its limits, driving improvements in graphics, sound, and input devices. The home computer was no longer just a tool. It was an entertainment system, an educational resource, and a creative canvas. Families gathered around computer screens just as they once gathered around televisions. Networking began spreading into homes and offices as well. Early networks allowed computers to share files, printers, and resources, but the most important development came from the growing use of modems. These devices allowed computers to communicate over telephone lines, connecting to bulletin board systems, BBS, early online services, and eventually something that was beginning to move from universities into the broader world, the Internet. At first, Internet access was slow, text-based, and limited to enthusiasts, but it introduced a powerful idea that computers were not isolated tools, but portals to a shared digital space. In offices and universities, local networks grew rapidly. Ethernet, a technology developed in the 1970s, became the foundation for most wired networks. It provided fast, reliable communication between machines and supported large-scale multi-user environments. Companies built server rooms to store data and run internal applications. Email emerged as a primary mode of communication, replacing memos and internal paper correspondence. The computer was no longer a standalone device. It was part of a connected ecosystem. As graphical interfaces matured, software became increasingly polished and accessible. By the late 1980s and early 1990s, the combination of GUI design, expanding software libraries, and growing peripherals created the modern desktop experience. Mice, graphical icons, window managers, printers, scanners, speakers, and modems all worked together to create an integrated environment. Instead of typing commands, users worked visually, intuitively, and interactively. These developments coincided with the steady advancement of microprocessors. Each new generation of chips offered faster performance, more memory, and improved capabilities. The Motorola 68000 series powered the Macintosh. Intel's 386 and 486 processors powered the PC revolution. RISC, reduced instruction set computing, architectures emerged, offering simpler yet faster instruction sets. Workstations built on RISC chips, like those from Sun Microsystems and Silicon Graphics, provided extraordinary computing power for graphics, engineering, and scientific work. The combination of GUIs, powerful processors, and expanding software ecosystems changed the identity of the computer. It was no longer a device for specialists or hobbyists. It was becoming a household appliance, a gateway to work, creativity, and communication. The barriers to entry were lower than ever. Children used educational programs. Adults used word processors and spreadsheets. Artists used design tools. Gamers pushed hardware forward. Students wrote papers, explored encyclopedias on CD-ROM, and dialed into early online networks. Computing was becoming a personal, universal experience, yet this period was only the beginning. While graphical interfaces made computers easier to use, another revolution was brewing, one that would reshape not just how people used computers, but how they lived, worked, and interacted with the world. A global network, once limited to universities and researchers, was about to open to the public, and when it did, it would transform computing from a personal tool into a shared digital universe. Chapter 9: The Internet Revolution and the World Wide Web. By the early 1990s, personal computers were already becoming fixtures in homes, classrooms, and offices. Graphical interfaces had made them accessible, software had made them useful, and growing processor power had made them fast. But most computers were still islands, productive, capable, and powerful, yet fundamentally isolated. The idea of computers communicating had existed for decades, but it was still limited to universities, research institutions, and specialized networks. What was coming next would dissolve those boundaries and transform computing into something far larger. The personal computer was about to become a window into a shared digital world. The roots of the Internet go back to the late 1960s, when the U.S. Department of Defense funded an experimental research network called ARPANET. Its goal was simple but ambitious: create a communication system that could continue functioning even if parts of it were damaged or disconnected. This required a new way of structuring communication, one that did not rely on a central authority. Researchers created the concept of packet switching, breaking messages into small fragments that could travel independently across a network. If a route was blocked, the packet would simply take another path. It was resilient, efficient, and revolutionary. Throughout the 1970s and 1980s, universities and research laboratories built networks using similar principles. During this time, two researchers, Vint Cerf and Bob Kahn, developed the TCP/IP protocols, the foundational language of the Internet. These protocols allowed different networks, built on different technologies, to speak to one another. With TCP/IP, individual networks merged into a global network of networks. On January 1, 1983, ARPANET officially switched to TCP/IP, a moment that is often considered the true birth of the modern Internet. Even so, the Internet of the 1980s was nothing like the one we know today. It was text-based, academic, and technical. You needed special software, a strong understanding of commands, and often a university affiliation to access it. There were no pictures, no easy browsing, and no casual exploration. Then, in 1989, a researcher at CERN named Tim Berners-Lee proposed a system to make global information easier to access and link. He called it the World Wide Web. Berners-Lee created three fundamental technologies: HTML for documents, HTTP for communication, and the URL for addressing. Together, they formed a universal framework for linking documents across a distributed network. The first website went live in 1991, and although it was simple and text-heavy, it held the blueprint for everything that would follow. The web introduced the idea that information could be navigated visually, intuitively, and interactively. It turned the Internet from a technical tool into a universal medium. The next major breakthrough came from the University of Illinois, where a team led by Mark Andreessen created Mosaic in 1993. Mosaic was the first popular graphical web browser. Suddenly, the web could display images alongside text, and users could navigate pages with a click. This single change made the web accessible to the general public. What followed was a period of rapid growth. Businesses launched websites. News organizations published online content. Libraries, universities, and museums created digital archives. The Internet was expanding beyond academia and becoming a part of everyday life. Commercial Internet service providers, ISPs, appeared, offering dial-up access to anyone with a phone line. Though slow and accompanied by distinctive modem sounds, this was the first time millions of people could connect from home. Email became a standard form of communication. Online message boards and early communities like Usenet and IRC attracted users from around the world. By the mid-1990s, the Internet was shifting from a curiosity to a global social and economic engine. In 1994, Andreessen co-founded Netscape and released Netscape Navigator, a browser that quickly dominated the rapidly growing web. Microsoft soon saw the significance of this new digital frontier and released Internet Explorer, embedding it into Windows. The result was the browser wars, a period of intense competition that accelerated innovation, but also led to legal battles over software bundling. Yet despite the corporate conflicts, the Internet continued to grow at an extraordinary pace. The late 1990s brought online commerce. Companies like Amazon and eBay demonstrated that the web could support entire businesses, not just information pages. Search engines evolved from simple directories to sophisticated indexing systems. Yahoo, AltaVista, and eventually Google helped people navigate the expanding landscape of online content. Streaming audio and early video clips appeared, though limited by bandwidth. Online multiplayer games connected players across continents. News, entertainment, and social interaction moved into digital form. As the web matured, user-generated content became increasingly important. Blogs, forums, and early social networking sites allowed people to express themselves and share information. Photo-sharing sites, digital communities, and early online journals laid the groundwork for the participatory Internet that would later define the 2000s. Even though computers of this era were limited by slower processors and dial-up connections, they opened the door to a world where distance mattered less and digital presence mattered more. The arrival of broadband Internet in the late 1990s and early 2000s accelerated everything. Faster connections enabled richer websites, streaming media, real-time communication, and cloud-based services. The web shifted from pages of text and small images to dynamic content, multimedia, and interactive applications. The idea of computing began to change. The computer was no longer just a tool for local tasks. It was a gateway to shared knowledge, entertainment, community, and commerce. The internet did more than connect computers. It connected people. It reshaped how we worked, learned, communicated, and explored the world. And after the web became mainstream, a new chapter began, one driven by mobility, portability, and constant connectivity. Chapter 10. Laptops, Mobility, and the Early Wireless Era. By the late 1990s, personal computers had become familiar fixtures in homes and workplaces. They were powerful, connected, and essential for communication, research, entertainment, and productivity. But they still shared one limitation. They were anchored to desks. The internet was expanding rapidly, yet access to it was confined to rooms with phone jacks or Ethernet ports. Computing had become personal, but it had not yet become mobile. The next phase of the digital evolution would break that final tether. Portable computing had existed for decades, but only in limited and often impractical forms. Early luggables of the 1980s, like the Osborne 1 and the compact portable Tome, were technically mobile, but they weighed as much as sewing machines and required heavy lead-acid batteries or wall power. Their screens were tiny, their performance modest, and their use cases narrow. They opened the idea of portable computing, but didn't fulfill it. True mobile computing emerged in the 1990s with the rise of laptops, machines that combined flat-panel displays, rechargeable batteries, compact hard drives, and integrated pointing devices. These components were the product of years of refinement. Liquid crystal displays, LCDs, replaced bulky glass CRTs. Nickel metal hydride and lithium-ion batteries improved energy density. Smaller hard drives and memory modules shrank storage components, and trackpads and track points matured into reliable input methods. One of the first major milestones was the IBM ThinkPad series, introduced in 1992. Known for its durability, matte black design, and distinctive red pointing stick, the ThinkPad became a staple in business environments. It represented a shift from portable curiosities to truly dependable mobile tools. Around the same time, Apple introduced the PowerBook, which reimagined laptop ergonomics by placing the keyboard near the screen and adding palm rests, a layout that would influence all future laptops. These machines helped define the modern portable computer. Light enough to carry, powerful enough for daily work, and capable of running the same software as desktop systems. But mobility did not fully flourish until laptops could connect without cables. Throughout the early 1990s, networking required Ethernet ports or dial-up modems. Wireless technology existed, but was slow, proprietary, and rarely standardized. That changed with the introduction of Wi-Fi, based on the IEEE 802.11 standards. Early Wi-Fi networks were limited to modest speeds, but they eliminated the need for physical connections entirely. By the late 1990s and early 2000s, wireless routers entered homes, offices, airports, coffee shops, and university campuses. This shift transformed how people used computers. You could check email from the kitchen, browse the web on the couch, work from a cafe, collaborate from a classroom. The internet was no longer confined to desks. It was drifting through the air. The Wi-Fi revolution also changed software expectations. Applications that once assumed sporadic connectivity began incorporating real-time communication. Email clients synced continuously. Browsers refreshed instantly. Collaborative tools emerged that allowed multiple users to view and edit documents together. Students brought laptops to class. Professionals traveled with them. Families shared them. Mobility became a defining feature of digital life. Meanwhile, processors designed specifically for laptops emerged, optimized for low power consumption and heat efficiency. Intel's Pentium M and later the Core series ushered in architectures focused on balancing speed and battery life. Graphics processors became more efficient. Solid-state drives, SSDs, still expensive, began appearing in high-end machines, replacing spinning disks with silent, shock-resistant storage. Operating systems evolved to support this new mobile ecosystem. Microsoft improved power management, plug-and-play hardware detection, and wireless network configuration in Windows 98, XP, and later versions. Apple's macOS, especially after the company transitioned to Intel chips in 2005, offered a refined, stable environment well-suited for portable computing. Linux distributions also grew in popularity among developers, aided by lightweight desktop environments suited for older laptops. The rise of mobility also changed how people interacted with digital information. Photos, documents, and music no longer lived exclusively on a single hard drive. USB flash drives made file transfer simple. External storage became common. Later, emerging cloud services enabled syncing files across devices automatically. A person could take a laptop on the road and still have access to their files, emails, and online accounts, something unthinkable just a decade prior. Laptops grew more capable each year. Screens became brighter and larger. Keyboards became more comfortable. Batteries lasted longer. Ports standardized. Machines grew thinner, lighter, and more efficient. The idea of work on the go became normal rather than exceptional. Students typed essays on trains. Scientists recorded field notes in real time. Professionals worked from hotel rooms. Families used laptops for movies, games, and communication. Wireless mobility also laid the groundwork for something even more transformative: the idea that computers did not need to be laptops at all. If connectivity was ambient, if the internet was available from anywhere, then computing could move into new forms: small, handheld, always-on devices. Early so personal digital assistants, PDAs, like the Palm Pilot, hinted at this direction. But it would take improvements in displays, processors, battery technology, and mobile operating systems before this idea could fully flourish. By the early 2000s, laptops had become the dominant form of personal computing. Desktops remained essential for gaming, graphics, and heavy workloads, but laptops were the machines people carried into everyday life. They supported work, leisure, learning, and communication. They enabled global travel, remote work, and mobile creativity. As wireless networks spread and mobile processors improved, the distinction between connected and not connected faded. The world was preparing for the next stage, the age of smartphones, tablets, and ubiquitous computing. These devices would push mobility even further, placing connected computers not just in bags, but in pockets, in hands, and eventually into everyday objects. The line between computers and communication devices would blur, and computing would move from something you did at a computer to something constantly present in your environment. Chapter 11: Smartphones, Touchscreens, and the Era of Ubiquitous Computing. By the early 2000s, laptops had made computing portable, and Wi-Fi had made connectivity mobile. But a deeper shift was unfolding, one that would fundamentally redefine how people interacted with digital technology. Computers were no longer confined to desks or backpacks. Screens were shrinking. Wireless networks were spreading, and the idea of a computer itself was beginning to change. The next revolution would not arrive as a smaller laptop, but as a device that fit in a pocket. Before smartphones emerged, PDAs, personal digital assistants, hinted at what mobile computing could be. Devices like the Palm Pilot, released in the late 1990s, offered calendars, notes, contacts, and simple applications. They used stylus-based input and monochrome screens. They weren't phones, and they weren't computers, but they were something in between: portable digital organizers. Around the same time, BlackBerry devices began gaining popularity in business environments. With miniature keyboards and robust email systems, BlackBerry phones created a new category of mobile productivity. Professionals could send messages, check schedules, and handle communication from anywhere. It was the first sign that mobile devices could compete with laptops for certain tasks. The real transformation began in 2007 with the introduction of the Apple iPhone. While other smartphones existed, the iPhone combined multiple technologies in a way that immediately changed expectations. It featured a large, capacitive touchscreen, eliminating the need for physical keyboards or styluses. It introduced a fluid, gesture-driven interface that made navigation intuitive. It merged a phone, an iPod, and an internet communicator into one device. And importantly, it presented the web as it was meant to be, seen not through simplified mobile pages, but full desktop-class browsing. 1 year later, the App Store launched, and the smartphone landscape exploded. Instead of relying solely on software pre-installed by manufacturers, users could download applications built by developers around the world. Games, tools, productivity apps, maps, streaming services, messaging platforms, everything could be installed instantly. The smartphone became not just a phone, but a customizable, endlessly expandable computer. Android, developed by Google, quickly followed. With its open-source foundation and partnerships with multiple manufacturers, Android offered a wide range of devices at different price points. Competition drove rapid innovation. Screens grew sharper. Cameras improved dramatically. Processors became more powerful. Mobile operating systems evolved into sophisticated platforms capable of running complex applications, multitasking, and cloud-connected services. This era also transformed how people communicated. Text messages gave way to multimedia messaging, video calls, group chats, and social networks. Platforms like Facebook, Twitter, WhatsApp, Instagram, Snapchat, and later TikTok created global communities where people shared experiences instantly. Communication shifted from scheduled interactions to continuous streams of updates. The smartphone made this possible because it was always with the user, always connected, always running apps, always collecting notifications. Mobile internet access further accelerated this transformation. Early smartphones relied on 2G and 3G networks, which enabled basic browsing and email. But the rollout of 4G LTE in the 2010s brought broadband-level speeds to mobile devices. Streaming high-definition video, real-time navigation, online gaming, and cloud applications became seamless. Suddenly, much of what people once needed a laptop for could be done on a smartphone. As processing power grew, so did the capabilities of mobile software. Devices incorporated high-resolution cameras, which replaced point-and-shoot digital cameras for most users. GPS enabled precise location tracking. Accelerometers and gyroscopes supported immersive motion-controlled applications. Biometric security, fingerprint sensors, and facial recognition made unlocking devices effortless. Each generation of smartphones packed more computing power into slimmer hardware, exceeding the performance of early personal computers. Tablets emerged as an extension of this mobile ecosystem. Devices like the iPad, released in 2010, created a new category between laptops and smartphones. Tablets offered large touchscreens, long battery life, and lightweight designs. They became tools for reading, drawing, watching media, and browsing the web. In educational settings, tablets replaced textbooks and paper worksheets. In creative fields, they became digital sketchpads. And in homes, they became general-purpose entertainment devices. Mobile computing didn't just change devices, it reshaped digital habits. People began using cloud storage services to synchronize photos, documents, and data across phones, tablets, and laptops. Apps replaced websites for many tasks. Voice assistants like Siri, Google Assistant, and Alexa introduced conversational interfaces. Notifications transformed attention patterns, drawing people into streams of information throughout the day. The smartphone era also catalyzed new industries. Ride-sharing, food delivery, mobile banking, fitness tracking, mobile gaming, and digital payments all emerged from the combination of mobility, connectivity, and app ecosystems. GPS and mapping technologies powered real-time navigation and location-based services. High-quality smartphone cameras reshaped journalism, photography, and social media culture. Entire workflows, from editing videos to managing businesses, shifted onto mobile platforms. At the same time, smartphones raised new challenges. Privacy concerns grew as devices collected vast amounts of personal data. Social media influenced behavior, attention spans, and public discourse. Screen time increased dramatically. Cybersecurity threats expanded as more sensitive information moved onto mobile devices. These challenges reflected the profound impact of smartphones. They were no longer tools, they were extensions of daily life. Yet, even as smartphones became the dominant computing platform for billions, another shift was beginning. Mobile performance was improving to the point where smartphones rivaled laptops. Machine learning accelerators appeared in mobile chips, enabling features like real-time language translation, advanced photo processing, and on-device AI inference. Wearables, smartwatches, fitness bands, augmented reality glasses extended computing beyond pockets and into clothing and accessories. The idea of ubiquitous computing had fully arrived. People no longer went on the computer. They were always connected, always within reach of digital tools, always interacting with an ecosystem of applications and services flowing through the air. The boundary between the physical world and the digital world had softened, and as smartphones matured, the next chapter began forming. The rise of cloud computing, big data, scalable services, and artificial intelligence. These systems would shift the center of computing power from personal devices to vast distributed infrastructures, redefining not what computers looked like, but where the real computation happened. Chapter 12. Cloud computing, big data, and the rise of scalable infrastructure. By the late 2000s, smartphones, laptops, and broadband connections had created a world where people were constantly interacting with digital information. Photos, messages, documents, music, and videos flowed across devices, networks, and platforms. But something subtle was happening beneath the surface. The center of computation was shifting away from personal hardware. Instead of storing everything locally, people began uploading, downloading, and synchronizing through remote servers. The computer you carried was no longer the only engine doing the work. A new backbone was forming, one built on distributed servers, virtual machines, and scalable systems that could expand as demand grew. This was the dawn of cloud computing. Although the idea of shared computing resources had existed since the mainframe era, the modern cloud emerged when companies like Amazon, Google, and Microsoft realized that their large-scale internal infrastructure could be offered as a service to others. Amazon, in particular, had spent years building distributed systems to handle its massive retail operations. In 2006, the company launched Amazon Web Services, AWS, providing storage, S3, and virtual machines, EC2, to developers worldwide. For the first time, any individual or business could rent computing power on demand without purchasing physical hardware. This model of computation was transformative. Cloud services allowed companies to scale up instantly during peak usage and scale down during quiet periods. Instead of investing millions in servers, cooling systems, and maintenance, businesses could pay only for what they used. This flexibility fueled innovation. Startups built applications without needing an in-house data center. Large companies modernized their infrastructure with a fraction of the cost. Developers could deploy code instantly, experiment freely, and collaborate globally. Google and Microsoft quickly expanded the cloud ecosystem. Google Cloud Platform, built on Google's internal infrastructure, provided powerful computing, machine learning tools, and massive storage capacity. Microsoft Azure integrated cloud technology with enterprise software, making it easier for companies to migrate from on-premises systems. Together, AWS, Azure, and Google Cloud created a competitive, rapidly evolving environment that supported millions of applications, websites, and services. Cloud computing also transformed consumer experiences. Services like Dropbox, iCloud, OneDrive, and Google Drive allowed people to store files online and access them from any device. Streaming platforms, Netflix, YouTube, Spotify, shifted media consumption from downloads to real-time playback. Email moved from local clients to web-based interfaces hosted in the cloud. Social media platforms operated entirely on remote servers, managing billions of photos, messages, and posts. People no longer needed to know where their data lived. It was simply in the cloud, accessible whenever needed. As cloud adoption grew, so did the volume of digital information. Every search query, GPS route, social media interaction, and online purchase generated data. Sensors in phones, cars, appliances, and industrial systems collected information continuously. The result was an unprecedented accumulation of digital records, what the industry called big data. Traditional databases could not handle the velocity, volume, and variety of this data. New tools emerged: Hadoop, Spark, NoSQL databases that could store and analyze massive datasets spread across thousands of distributed servers. Big data analytics allowed companies to uncover patterns, optimize logistics, predict customer behavior, and improve operations. Retailers used purchase data to refine inventory. Hospitals analyzed medical records to identify trends and improve care. Scientists processed large datasets to study climate patterns, genetics, and astronomical observations. Governments used analytics for planning, infrastructure, and emergency response. The ability to process information at scale opened doors to insights impossible with traditional computing. Cloud infrastructure also introduced new ways of organizing software. Instead of running applications as monolithic programs on a single server, developers adopted microservices, breaking applications into smaller components that could scale independently. These services ran inside lightweight containers, often managed by platforms like Docker and Kubernetes, that could be deployed instantly across distributed environments. This containerized approach created more resilient, flexible, and scalable systems. The shift to scalable cloud infrastructure reshaped the nature of computing work. Companies once reliant on physical servers transitioned to virtualized environments. Administrators managed clusters of virtual machines instead of racks of hardware. Developers embraced continuous integration and continuous deployment pipelines, allowing them to push updates rapidly and safely. The line between hardware and software blurred as infrastructure became programmable, defined not by physical components, but by code and orchestration tools. This period also saw the rise of serverless computing, where developers wrote functions that ran in response to events, without managing servers at all. Platforms like AWS Lambda abstracted infrastructure so completely that the concept of a server became invisible. Developers focused solely on logic, while the cloud handled scaling, execution, and reliability. This model dramatically simplified development and lowered the barrier to entry for building complex applications. Despite its benefits, cloud computing introduced new challenges. Security became a central concern as sensitive data moved to remote servers. Companies had to adopt encryption, identity management, and multi-layered defenses to protect information. Outages in major cloud providers occasionally caused widespread disruptions, revealing the risks of concentrating so much digital infrastructure in a few global platforms. Privacy concerns also grew as companies collected vast amounts of user data, raising questions about consent, surveillance, and regulation. Yet the momentum behind cloud computing was unstoppable. It powered everything from social networks to streaming platforms, from online education to global collaboration tools. It provided the foundation for gaming platforms, cryptocurrency networks, scientific simulations, and enterprise applications. By the mid-2010s, The cloud wasn't just a trend, it was the central nervous system of the digital world. This shift set the stage for the next major evolution, the rise of artificial intelligence. AI required massive computational power, enormous data sets, and efficient distributed systems, all of which the cloud supplied. As machine learning models grew larger and more capable, cloud platforms expanded with specialized hardware, GPUs, TPUs, and high-performance compute clusters designed specifically for AI workloads. These systems would shape the next chapter of computing, transforming everything from search engines to healthcare, automation, robotics, and creative tools. Chapter 13: Artificial Intelligence, Machine Learning, and the New Computational Frontier. As cloud computing matured and big data systems spread across the world, a new transformation began rising on top of them, one that would redefine what computers could do, not just how they were built or where they lived. This was the resurgence of artificial intelligence, powered not by speculative theories or small research projects, but by massive datasets, specialized hardware, and distributed cloud infrastructure. For decades, AI had existed mostly in academic labs, fueled by cautious optimism and occasional bursts of progress. But by the late 2010s, the world was finally ready to support AI at scale. To understand why this era was different, it helps to look back. Early AI research in the 1950s and 1960s focused on symbolic reasoning, teaching computers to follow logical rules, manipulate symbols, and solve problems like mathematicians. These experiments were inspiring but limited. Real-world intelligence required something more flexible. The next wave came from neural networks, inspired loosely by the structure of the human brain. Neural networks could learn patterns directly from data, but early computers were too weak to train large models. For decades, progress came slowly. That changed in the 2000s, when three critical ingredients converged: powerful GPUs originally designed for gaming, massive datasets created by the internet, and cloud infrastructure capable of training models across thousands of servers. This combination sparked a new era known as deep learning, where neural networks with many layers could recognize speech, classify images, translate languages, and model complex relationships. Training these networks required enormous computation, something only large clusters of GPUs or specialized hardware could deliver. Fortunately, the cloud made that power accessible. One of the early breakthroughs came in 2012, when a deep neural network developed by researchers at the University of Toronto dramatically outperformed traditional methods in image recognition. This moment confirmed what many suspected. Deep learning was not just an academic curiosity, it was a breakthrough capable of transforming software. Suddenly, AI systems could see, hear, and understand patterns with remarkable accuracy. Industry moved quickly. Google, Microsoft, Facebook, Amazon, and countless startups began building large-scale AI systems. These models powered voice assistants like Siri, Alexa, and Google Assistant. They improved search engines, recommendation systems, translation tools, and speech-to-text interfaces. Email spam filters, navigation apps, and fraud detection systems all began incorporating machine learning. Instead of manually programming rules, developers trained models on vast datasets, letting them learn patterns automatically. As neural networks grew larger, researchers developed specialized hardware. NVIDIA's GPUs became the de facto standard for training models. Google created tensor processing units, TPUs, chips optimized specifically for neural network operations. Other companies built AI accelerators for data centers, smartphones, and edge devices. Moore's law was slowing, but AI workloads benefited from parallel operations and specialized architectures, creating a new era of performance scaling. By the early 2020s, AI entered yet another chapter with the rise of large-scale generative models. These models, trained on enormous datasets of text, images, audio, and video, could generate content, answer questions, summarize information, create code, and assist with complex tasks. Systems like GPT, diffusion image models, speech synthesizers, and multimodal networks showed that AI was no longer limited to classification and prediction. It could now produce creative, coherent, and useful outputs. This shift led to the rise of AI assistants, tools capable of holding natural conversations, performing research, helping with writing, analyzing documents, generating artwork, and automating workflows. These models were not perfect. They made mistakes, hallucinated details, and required careful supervision, but they represented a profound step forward. For the first time, AI began acting less like a tool and more like a collaborator. At the same time, machine learning moved beyond cloud servers and into everyday devices. Thanks to mobile accelerators and efficient architectures, phones could run on-device AI for face recognition, photo enhancement, voice dictation, and augmented reality. Smart home devices used AI to process speech. Cars incorporated AI for driver assistance, object detection, and navigation. Wearables analyzed health patterns. Even household appliances used machine learning for energy efficiency and automation. This rise of AI also transformed scientific research. Machine learning models analyzed genetic data, simulated chemical reactions, accelerated drug discovery, and processed astronomical observations. Climate scientists used AI to model weather systems and predict extreme events. Engineers used AI to optimize designs. Mathematicians used AI to explore patterns in large datasets. In many fields, AI became a multiplier, an engine that helped researchers push beyond previous limits. At the same time, AI raised complex ethical, social, and regulatory questions. Who owned the data used to train models? How should bias be handled when datasets reflect real-world inequalities? What rights should people have over content generated by AI systems? How should society balance AI-driven automation with employment and economic impacts? These discussions grew as AI became more powerful, prompting governments and industry organizations to develop guidelines, standards, and regulations. Despite the challenges, AI continued expanding. The models became smarter, the hardware faster, and the applications more widespread. Companies integrated AI into customer support, logistics, software development, cybersecurity, and healthcare. Creative industries adopted AI for design, storytelling, video production, and music composition. Education platforms used AI tutors. Financial systems used machine learning for analysis and forecasting. Everywhere data existed, AI found a role. The rise of artificial intelligence set the stage for the next major shift, computation moving beyond individual devices and into the distributed, augmented fabric of daily life. Smart homes, autonomous vehicles, wearable sensors, and connected infrastructure all pointed toward a future where digital intelligence appears not just on screens, but in the environment around us. With AI accelerating and cloud computing maturing, the next chapter of computing would explore the integration of physical and digital worlds through the Internet of Things, edge computing, and the emergence of pervasive ambient intelligence. Chapter 14. The Internet of Things, Edge Computing, and the Age of Connected Everything. As artificial intelligence accelerated and cloud platforms expanded, another transformation was quietly unfolding, one that moved computing beyond screens and into the physical world. People were no longer interacting with computers only through keyboards, touchscreens, or browsers. Instead, everyday objects were beginning to collect data, communicate wirelessly, and operate with digital awareness. This new layer of technology, embedded into appliances, vehicles, sensors, cameras, and infrastructure, became known as the Internet of Things, or IoT. It represented a shift from using computers to living among them. The idea behind IoT was simple. If everyday devices could connect to the Internet, they could provide real-time data, automate tasks, improve efficiency, and coordinate with one another. Early examples were modest RFID tags in warehouses, simple environmental sensors, and smart thermostats. But as wireless networks, low-power chips, and embedded processors improved, connected devices spread rapidly. Doorbell cameras streamed live video. Light bulbs adjusted automatically to time of day. Security systems sent alerts to smartphones. Refrigerators tracked expiration dates. Speakers became digital assistants. Homes slowly transformed into systems of sensing, automation, and remote control. Industry saw the potential even more clearly. In factories, IoT devices monitored machinery, predicting failures before they happened. In agriculture, soil sensors optimized irrigation and crop management. In logistics, fleets of vehicles reported location, fuel usage, and engine health in real time. In hospitals, connected medical devices tracked patient vitals continuously. Cities installed smart streetlights, traffic sensors, and environmental monitors to improve transportation and reduce energy consumption. Every sensor generated data, and every piece of data became part of a larger system that could optimize, automate, and inform. However, this explosion of connected devices created a new challenge: latency. Many IoT systems required immediate responses, far faster than cloud servers on the other side of the world could provide. A self-driving car could not afford a half-second delay, while a remote server processed sensor data. A factory robot could not wait for a distant data center to approve a movement. Homes needed instant automation. Hospitals required reliable, real-time monitoring. The solution was edge computing. Instead of sending all data to the cloud, edge computing processed information closer to where it was generated, on local servers, gateways, or even the devices themselves. This reduced latency, improved reliability, and eased the burden on cloud networks. A camera could analyze video locally to detect motion. A car could process sensor data on board to make split-second decisions. A warehouse robot could coordinate with its neighbors using local communication. The edge became a distributed extension of the cloud, bringing intelligent processing directly into the physical environment. This model shaped the next generation of device architectures. Processors designed for machine learning inference appeared in everything from smartphones to home appliances. Specialized chips, tiny yet powerful, ran neural networks directly on IoT devices. Privacy improved because data no longer needed to leave the device to be processed. Energy efficiency increased. Real-time responsiveness became normal. As IoT and edge computing expanded, consumer expectations changed. People began assuming that devices should respond instantly, predict needs, automate routines, and integrate seamlessly into daily life. Smart homes adjusted lighting and temperature automatically. Wearables tracked health metrics continuously. Cars downloaded software updates over the air. Appliances scheduled themselves around energy usage patterns. Even simple objects, locks, thermostats, plugs, and sensors gained computational awareness. This era also introduced complex new challenges. Security became critical because every connected device represented a potential entry point for attackers. Millions of low-cost IoT devices lacked strong security, making them vulnerable to malware and botnets. Privacy concerns grew as cameras, microphones, and sensors collected constant information. Interoperability issues surfaced as devices from different manufacturers struggled to communicate. These challenges pushed the industry to develop standards, encryption practices, and regulatory frameworks to ensure safe deployment. Despite the challenges, IoT continued to expand into infrastructure. Smart grids optimized energy distribution. Traffic systems adjusted signals to reduce congestion. Environmental sensors monitored air quality. Water systems detected leaks automatically. In industrial settings, IoT became central to automation, predictive maintenance, and robotics. Companies used digital twins, virtual models of physical systems, to simulate performance and plan improvements. Airports, factories, farms, and entire cities embraced IoT to streamline operations and reduce waste. At the same time, wearables became increasingly sophisticated. Smartwatches measured heart rate, blood oxygen, sleep patterns, and step counts. Fitness trackers encouraged activity. Medical wearables monitored chronic conditions. These devices blurred the line between technology and wellness, integrating computing into the most personal aspects of daily life. Automotive computing also evolved dramatically. Cars incorporated networks of sensors, cameras, radars, and LiDAR units feeding data into onboard processors. Driver assistance systems used AI to maintain lane positioning, detect obstacles, and adjust speed. Fully autonomous driving remained a long-term challenge, but the foundations, sensor fusion, real-time mapping, edge inference, were all products of IoT and machine learning blending together. This period marked a profound shift. Computers were no longer objects we interacted with occasionally. They became silent companions embedded in the environment, constantly collecting information, making decisions, and responding to changing conditions. The physical world gained a digital shadow, a parallel layer of data and computation woven into homes, workplaces, transportation, healthcare, and public infrastructure. The rise of IoT and edge computing set the stage for the next transformation, a world where devices not only communicated but collaborated, where augmented reality, wearable displays, smart environments, and interconnected systems formed a seamless digital ecosystem. With sensors everywhere, AI running locally, and cloud infrastructure orchestrating it all, computing was moving towards something more immersive and ambient. And the next chapter would explore how all these layers, mobile devices, connected sensors, cloud intelligence, and AI at the edge converged into the era of augmented reality, virtual worlds, and blended digital physical experiences. Tonight, you've walked farther than you realize. You began among warm vacuum tubes and humming relay switches, in rooms where machines filled entire floors and spoke only in the clack of punched cards. You crossed into the age of transistors, smaller than a fingernail but powerful enough to pull humanity out of its mechanical past. You drifted through mainframes the size of cars, through the birth of programming languages, and into the early networks that whispered the first messages across copper lines. You moved gently into the era of home computers, machines that blinked awake on family desks, glowing in the dark like small promises of the future. You passed the rising arc of personal software, the first digital art, the earliest spreadsheets, the quiet magic of code that began shaping modern life one keystroke at a time. You followed the path of chips as they shrank, split, and reorganized themselves into intricate towers of silicon. You watched as laptops folded the desktop world into something portable. You drifted into the first wireless signals, into the rise of the global internet, into the moment when everything, work, communication, creativity, memory, slipped into the clouds. Then the world shrank again. Phones learned to think, cameras learned to see, and the devices in our pockets became inseparable from the fabric of daily living. Sensors appeared in lamps, thermostats, cars, streets, small watchful nodes inside a planet quietly stitching itself together. From there, the future leaned forward. Virtual worlds formed. Quantum machines began to whisper in laboratories. Neuromorphic chips started to mimic the rhythms of living neurons, and artificial intelligence stepped into the foreground, analyzing data, writing text, generating images, solving problems once thought impossible. And now, here you are. Not on the factory floor where the first transistors blinked, not in the quiet labs where ENIAC's panels warmed the air, not beside the blinking modems of the 1990s, not in the server farms where clouds breathe. You're in the present, a world built on layers and layers of ingenuity, carved by decades of engineering dreams, carried by millions of small breakthroughs that all pointed forward. And the remarkable thing is, the journey isn't finished. Somewhere at this moment, a chip is being designed with structures measured in atoms. Somewhere, a new algorithm is learning to solve problems even its creators can't fully explain. Somewhere, a quantum bit is holding two states at once, cutting through a problem that would take classical computers centuries. Somewhere, a neural network is tuning its billions of parameters into a shape that can speak, draw, drive, plan, or translate. Somewhere, the next chapter is already being written. But tonight, you don't need to go there yet. Tonight is about letting the entire history settle into a soft, steady hum. The same hum the earliest machines once gave off. It's about recognizing that every step of this journey, from tubes to transistors to AI, comes from the same simple human desire to understand, to create, to expand what's possible. Computers are fast, cold, and logical. Humans are slow, warm, and imaginative. Together, something extraordinary happened. The world changed, and it's still changing. So let the story rest here for now. Let the machines idle in the background, their gentle electric heartbeat fading to a distant rhythm. Let the timelines, breakthroughs, inventions, and discoveries blur softly into one long thread. A quiet, decades-long exhale from a planet that learned how to think in silicon. You've traveled from the beginning to the edge of the future. You've crossed the entire landscape of computing, from one era to the next, until the present feels a little clearer, a little calmer, a little more connected. Now all that's left is stillness. Let the history drift to the back of your mind. Let your breath fall into a slow and easy pattern. Let your thoughts soften like old pixels fading gently on a screen. You've gone far enough for one night. Close your eyes. Rest. The next chapter of computing will be there in the morning.